Okay, so let's get started. Let me share my video. All right. Okay. Cool. Okay, so let's get started. Yeah, so like I said, the recitation for today covers one problem in hypothesis testing and and then we're gonna spend the rest of the recitation to derive the coefficients of linear regression. Specifically, it's the ordinary least squares, OLS, and we're gonna see where those derivations come from rigorously. Okay, so let's start with the theorem. So this is going to be theorem 9.7.3 first. So in this theorem, first of all, we observe data, right? So the problem is gonna say here's a random sample. So let's start random sample. And then say you have x1, x2, all the way to xn. And then maybe this is, say it's like, I'm going to use a notation called M. So this random sample has M observations. And then same thing, that you observe another sequence of random samples. Let's call them Y. So observe another random sample. I'm going to call it Y1, Y2. And maybe this other random sample has a different sample size, right? They don't have to be the same. So instead of M, we call it N. And maybe this means N observations. And then for the first sequence, let's say it's a normal distribution. So this is from normal. Normal has two parameters, right? Mean and variance. So we're gonna say with mean, mu1, and variance, sigma 1. And let's say this is unknown. And same with the second sequence, we have mean and variance. So this is from distribution with mean, this is going to be mu2, and the variance is going to be sigma 2, and of course unknown. So in this setup, we observe two samples, and the goal is to do a hypothesis testing. So I say the goal is to do hypothesis testing, specifically with the following statement of the hypothesis. So null hypothesis, the first statement says the variance from the first sample is less than variance from second sample. So that's a null hypothesis. Of course, we're going to have an alternative hypothesis. So versus the alternative hypothesis H1 is going to be the other way around, so greater. So sigma 1 squared greater than sigma 2 squared. So in this case, the setup and the computation is actually very easy, and we'll write it out. So in this theorem, the first thing that you do is you compute the sample variance of both of these random samples. Okay, so the first thing, sample variance. And then we're going to take ratio of the sample variance, and that ratio is going to be the test statistics. All right, so let's write it out. So what do you do here? So first compute. First compute sample variance for X, and which is going to be, we're going to use the notation of this to be the sample variance. Sorry, this S of X to be the summation. I'll just write it out. So it goes something like this. So the S of X is something like summation xi, x bar, something like that. And then because of sample variance, so we have to do basically divide everything by the sample size minus 1. So that will be m minus 1, and there'll be m minus 1. All right. So the shorthand notation, because usually problem will tell you. So the shorthand notation, we're just going to be this part. All right. So I'll erase the one part on the right, and that's going to be the shorthand notation. And same with the other random samples. So also compute sample variance for y. And that's going to be equivalent to x. It's going to be something like this, m minus 1. All right. So now you have the sample variance for two sequence of random samples, random data. Now we're going to compute. So next, compute test statistics. In practice, you call it whatever you want, but I'll just use a textbook notation. It's noted as V. I think it's kind of like a short name for variance. So it's kind of easy to memorize, V, variance. And it's essentially the ratio of these two sample variants. So let's write that out. This is Sx over m minus 1 over Sy over n minus 1. That's 1. Okay, so now the theorem states that this V, okay, under essentially null hypothesis, it's actually a F distribution. So theorem states V, all right, so theorem states under null, V has F distribution. Specifically, F distribution has what? 2 degrees of freedom, right? That's the definition of F distribution. So you can kind of guess, right? The 2 distribution corresponds to the bottom part of the sample variance. So this is a m minus 1, n minus 1. So in other words, what is this theorem trying to tell us? So this theorem trying to say, okay, we have a situation, right? 2 samples, right? 2 samples. We compute the sample variance. We have formula for that. And we know the degree of freedom, right? n minus 1, n minus 1. If your null hypothesis is true, it should just be F distribution, done. If you work out the math, it turns out that the whatever test statistic result that you cook up, it's so much bigger than the critical value of that F distribution under a certain significance level, then the evidence points to the alternative hypothesis. Okay, so we're going to take a look at an example. But here, just, let's wrap up this theorem by saying we reject null if V is greater than C. And let me just say a little bit about this, what a C is. A C, where C is a critical value from F distribution with the degrees of freedom n minus 1, n minus 1, assuming a certain significance level. Okay, so that's essentially what the theorem says. I wrote out a lot of details, so it looks long, but really the important part is usually the problem will give you this, right? It tells you what you want to do. And then really the only math that you have to know is essentially this part. So once you compute this part, you're pretty much halfway home. The rest is just to check the table, see what's going on with the critical value, you compare them, see which one's bigger and smaller. And that will tell you how to, reject or don't reject, right? So let's take a look at an example. So in this example, we're going to observe it's a two samples, right? So let's say you observe x1, x2 to x6. So this is going to be what? So you can kind of think that this is m is equal to 6. And then it tells you that the variance, the sample variance, s of x. I keep saying variance. This is technically speaking the summation term without dividing by m minus 1. So this is technically speaking the sum of the square. So it's like s. So it tells you that this is 30. All right. So the second sample, y1, y2, all the way to, I believe it's different sample size. So y21. This is, and obviously is 21. That's the sample size. And the problem tells you what is the sy. This is going to be 40. All right, so now the math is very simple. So you compute. Actually, before I write that, let me write out the hypothesis. So the goal is trying to determine is this, or versus alternative is this greater. All right, so we follow the theorem, right? So we compute this V, which is the test statistic. It's the ratio between two sample variance. So we're gonna do S of X divided by M minus 1 over S of Y divided by N minus 1. And this is going to be 30 divided by 6 over 40 divided, oh, I'm sorry, this is not 6. That is my mistake. It's a 6 minus 1, so it should be 5. And then the bottom is 21 minus 1. So that's 30 divided by 5 over 40 divided by 20. Make sense? So it's essentially 6 over 2, so that's 3. Okay, so as you see, the math is relatively easy because usually the problem is not gonna, they're not gonna ask you to compute the variance step by, like they're not gonna do something like this. Like they're not gonna do something like this. And then you have to like work out each one of them. And then if this is 6, then it's like I from 1 to 6, then that's gonna take forever, right? If it's 20, it's gonna take forever. So usually the problem is not gonna tell you that, it's just gonna tell you the result directly, which is kind of nice. So tell you the result is 30 divided by degrees of freedom, so n minus 1, because the sample variance is not just variance. And now you have the test statistics, which is this ratio between two sample variance. So then you can essentially check. So check. And here we assume, say 5% significance. All right. And then if under that assumption, the F distribution, essentially you can write something like this. This is, we use this notation. So the shorthand notation is the first degree of freedom, n minus 1, the second degree of freedom, n minus 1, and then this is the quantile. Quantile is 1 minus the significance level, all right? So this gives you, let's write that out. The first one is what, 6 minus 1, so what is that? That's 5. And the second one is 21 minus 1, so that's 20. 0.95. So this is about, that's not equal, my bad. That is approximate 2.71, something like that. Now you can say, okay, since V equals to 3, which is greater than 2.71, that is your F statistics, 520, 0.95, then conclude. What can we conclude? Since 3 is greater than the critical value under the significance level the problem provides us, then you can say reject null hypothesis. So then conclude reject null at 5% significance level. Make sense? Any questions about this part?
No, all good so far.
Good, awesome. Cool. Let's continue from here. The next problem, we're gonna dive into linear regression because the semester is fast. I look at the schedule. I was like, wait a second, like the final is scheduled on December 1st, and it doesn't really give you guys a whole lot of time to to study the material. But yeah, we're trying our best to catch up. So yeah, so let's get started with linear regression. I would probably say, just before I start the math, I would probably say this is the most important part of essentially your entire statistical career, which is to understand. First of all, you have to understand linear regression and how the coefficients are derived. But that's the basic part. Anyone with a calculus degree, with the calculus class taken, they can figure this out. But I want to point out that as we're going through the steps, it's really important to draw the connection between the derivation of searching for MLE and the derivation of linear regression, because really that's where the that's where the story comes from. I can't imagine someone will magically figure out linear regression and derive the coefficient of linear regression without thoroughly understanding MLE. So it's kind of like the same mathematical brain behind it. And when we're deriving it, I'm going to point out for you guys, why that's important. It's also good for memorization. So you just memorize one thing and you can figure out both. So it's a little bit more efficient as well. Okay, so that's enough chit chat. Let's get started. This is linear regression. So in linear regression, the conventional setup is, suppose you have data. I'm just going to use this bracket 1, parenthesis 1, x1, y1. That's like a sample. And then you have x2, y2. Maybe that's another sample, right? Keep going, all the way to xn, yn. So together you can kind of think of it as n samples. So here we say n samples. Okay, and then linear regression is essentially to fit the regression line. So what is a regression line? So fit the model. Y equals to beta 0, so plus beta 1, x. Right now we're writing it down, so it's not completely clear. On paper, when we write a vector form, so vector form, it's like capital Y and capital X. So this basically means what? This basically means it's like a vector, so something like this, with those little data points that the problem gave you. So y1, y2, yn, right? You guys got the idea. So it's like capital letter is a vector, small letter x and y, it's one data point. So that's x1. Maybe this is a little bit clear, just to distinguish, if we're talking about a vector or if we're talking about just one numerical data point. So in a model, I'm just writing y. So technically speaking, that's like a vector, right? So that's kind of I'll keep that in mind. We're not fitting one data point, we're fitting n samples. Okay, so the question is, what's the best? Now this best, we need to define that, right? So what's the best model? So best model basically referring to the best beta 0 and beta 1 such that some magical things happen, right? So this is a little bit of the machine learning brains in here. So what do we mean by the best, right? What do we mean by best? First thing is, the first question is note. First thing is note, parameters. Or you call it the coefficients. These are the things that we are able to change, right? If I tell you the data is x1, y1, you can't change that, right? Like it's given to you, you observe that, you can't just magically change it. But what you are allowed to change is beta 0 and beta 1. So let's write that down. All right. So now we know that we are allowed to change that. what is the next thing that we need to define to derive this beta 0 and beta 1? It's called, well, in machine learning, it's called a loss function or error function. In here, it's called a least square. So least square error. So we're going to write that out. Least square error. This is actually related to ordinary least square. So recall OLS. OLS essentially refers to ordinary least square, and that's where the terminology is coming from. Okay, so least square function. Let's just use a textbook notation. It's called Q, and this Q is defined as And this Q is defined as the summation I from 1 to n parentheses yi minus beta 0 minus beta 1 xi squared. So essentially, it's kind of like it kind of takes the philosophy of so we have sum I, and this is our truth, subtract our guess squared. So that's kind of where the philosophy is coming from, right? So I have our ground truth, and then I have our educated guess, right, which is this magical, linear model, right? The beta 0, plus beta 1 xi. The difference of those is going to be the mistakes that this model is making. Okay, so why do we need to know that? Well, the parameters and the coefficients beta 0 and beta 1 are derived based on the assumption that we want to minimize this mistake. Okay, so that's essentially where the story is coming from. So with that being said, now you can kind of essentially write something like this. So the objective is going to be minimize this Q by controlling beta 0 and beta 1. And this Q is essentially this formula, right? So this means, I'll write out here. So this means I want to minimize. This is your loss function. And this is by controlling beta 0 and beta 1. Right, so that's the big picture. That's the agenda, right? Now, with that being said, we can go into a little bit into the math and see how that's derived. So recall that in the MLE, we essentially take the partial derivative set to 0, and then we solve the MLE to be x bar, right? If it's the normals, you solve for x bar. So it's kind of the same framework, but a little bit more complicated. So let's take a look at that. So now we have the agenda. Now we need to take a look at so the idea is this Q. So take partial derivative of Q, which is what? Summation I from 1 to n yi minus beta 0 minus beta 1 xi squared. Okay, so here, take a partial derivative. So the first question is with respect to what, right? Well, we have two parameters. So if we take a partial derivative, it's with respect to the first one, right, beta 0, and then the second one, beta 1. And you need to do both of them, right? If you only do one of them, then you're not done, right? You only solve one of them. So let's try. First, let's do partial beta 0. This is your loss function Q. So this is taking the partial derivative with respect to beta 0 of whatever this Q is, right? Summation I from 1 to n yi minus beta 0 minus beta 1 xi. All right. So let's write that out. So derivative, right? Derivative. So summation, that stays the same. And then this 2 comes out, right? Comes out here. Because, if you do x squared, then that's like the x squared, prime is 2x, right? So 2 comes out. So I can write 2 here, right? And then whatever is in the middle, I can copy that down. But then here, since you're taking a derivative with respect to beta 0, so don't forget chain rule, right? So technically speaking, like if you're doing something like f g of x, you take prime, then it's like f prime, and then once you're done, you take g prime, right? So that's the chain rule part. So this part, we need to take care of that, which is essentially this term, because this is with respect to what? Beta 0. So once you do that, the negative sign will come out just like that. And let's write this a little bit better. So I'm going to remove that and write this minus sign here. Make sense? And now, once I'm here, I'm going to set it to 0 and then solve it, right? So so now I'm going to set this to 0. So what I'm going to do is I'm going to say set to 0. All right, and that's my first formula. So now I need to write out the second formula. So partial beta 1 q, and that is going to be partial beta 1, whatever q is, right? Summation I from 1 to n yi beta 0 minus beta 1 xi. Don't forget the square. And same thing, we're taking derivative of the whole thing. So what that's going to become is summation I from 1 to n yi beta 0 minus beta 1 xi. Square terms comes up front. So squares here, don't forget that. Now this part is a chain rule, right? Chain rule is what? Chain rule is essentially this part. Oops. You need to take care of this part, right? So notice that we are taking partial derivative with respect to beta 1. So when you take the derivative beta 1, let me do a drag here. So let's say you do this thing. And this is with respect to beta 1. Then this is just going to be x1, right? So kind of like 2x prime is what? Just 2. But the variable here is not on x1, it's on beta 1. So it comes out, so the constant term is actually x1. Okay, so I've seen people make mistake here. So that's just a little bit small caveat, taking derivative. Just pay attention of the notation. And what are you taking with respect to? And so you have to write xi here, okay? And don't forget the minus. I almost forgot that. And the same thing, set to 0. All right, so now this is a little bit clear, right? So what do we have right now? We have what? 2 equation, 2 unknown, right? So maybe that's equation 1. You call that equation 2. And then 2 unknowns, right? Beta 0, beta 1. So now we're gonna do a little bit of derivation. So bear with me. So now we're gonna start with beta 1, equation 1. So from 1, okay, what do we have? So let us simplify first. So we're gonna do summation I from 1 to n. This 2 is a constant term, and this is 0. So if I get rid of this 2, and it's like divided by -2, divided by -2, this is still 0. It doesn't change anything, right? So I can just scratch this part. So let's do that. This is apply I, and then here, this is a parenthesis. So if I want to open this parenthesis, I need to distribute this summation term in here, and then in here, and then in here, right? So let's try that. This is going to be summation yi, that's our first term, minus, technically speaking, it's going to be summation I from 1 to n beta 0. But that essentially just n of them, right? Because I doesn't, like beta 0 doesn't have like the rounding index I in there. So if I have n terms, add together, that's just going to be n times beta 0. So when you distribute this to the second term, it will give you n beta 0. So let's write that down, n beta 0. All right, and the third term is the same. So third term is something like this. Beta 1, that's a constant. So I'm going to leave that out. And the summation term, I can directly pass in here. Okay, so that becomes summation I from 1 to n xi. And the right-hand side is, of course, equal to 0. Okay, so we're gonna, so whatever, like we're gonna call this 3 or something, just to help us keeping track of what's going on. And the same thing with equation 2. So from 2, we're going to simplify a little bit. So 2 is what is here, right? First thing we're going to do is scratch out this -2 because as a constant term, if I divide by 2, -2 divided by -2 is 0, doesn't change anything. So let's scratch that. And then we're going to distribute this, right, just like that. And we're going to write it out. So summation I from 1 to n. The first term is what? This and this, right? So xi, yi. Right? And then what do we have? The second term is what? Xi and beta 0. So let's write that out. Minus beta 0 summation I from 1 to n xi. And then the third term is what? These and this, right? Together. So let's write that out. This is minus beta 1 summation I from 1 to n xi squared. And right hand side, it's equal to 0. Right? So that's going to be our equation 4. So now we can just rearrange the equation a little bit. So we say from 3, I'm going to rearrange such that beta 0 stay on one side, everything else move to the other side. Right? That's the goal. So what I'm going to do is I'm going to move this to the right hand side, and then I'm going to rewrite that so that the beta 0 stays on one side and everything else stays on the other side. So this is going to be n beta 0 equal to summation I from 1 to n yi minus beta 1 summation I from 1 to n xi. And I want to make things a little bit better. So I'm going to erase this n and then move it to the right hand side by doing something like this. Now you notice that this is actually just a y bar, right? And this is actually just x bar. So with that realization, we're gonna write this as y bar minus beta 1 times x bar, right? So now that looks much better, right? It's like, much simpler, easy notation, and we're gonna use that in the end. So I guess we can call it 5. So equation 5, right? Now we're almost there. Now what we need to do is derive what we have for this guy, and we're going to make that simpler. Okay. So what we do is we plug 5 into 4. So we're taking this, we're plugging in this place here, which is beta 0, right? So then the reason to do that is we kill one of the parameters and we solve for one equation, one unknown. So plug 5 into 4, what does that become? Let's open up a new page. So thus we have, let's be careful here. So essentially we're gonna copy down this equation, but this beta 0 we're gonna replace with this guy, all right? So so let's try that. So what I'm going to do is I'm going to crop all of these, and I'm going to copy. I'll paste it here, and I am going to essentially move this to the right, give myself some space, and then inside this beta 0, I'm going to erase that and replace with basically this thing, right? So let's write that out. This is going to be y bar minus beta 1 x bar, right? So we just did exactly that, plug 5 into 4. Okay, so now we have one equation, one unknown, right? So the rest is essentially just to, open up the parentheses, rearrange a little bit, see if we can derive something that looks pretty, right? So let's try that. So, okay, so I don't like the parentheses. I'm going to try to open this up. So let's try that. This is summation I from 1 to n xi yi. Okay, so open the parentheses. The first thing is what? Y bar. So y bar times summation I from 1 to n xi. All right, so that's the first thing. Second thing is the second term in parentheses times this thing. All right. So minus minus, that becomes plus beta 1, that stays the same. And then x bar, and then summation I from 1 to n xi. Okay. And the last term doesn't really change. So I'll just copy that down. And equal to 0 doesn't change. Right. So now, after we do this, you realize that there's a beta 1 here. There's not beta 1 here. And that's it. So we can essentially factor this one out and put these two things in the parentheses. All right. So let's try that. Summation I from 1 to n xi yi minus y bar summation I from 1 to n xi. Well, these two terms doesn't change, right? This doesn't change. So let's copy that down. Plus, now we said we're going to factor this one out, right? Factor this out. So beta 1 comes out. And in the parentheses, we have what? X bar summation I from 1 to n xi minus summation I from 1 to n xi squared equal to 0. All right. So so now we are at a place where things get a little bit trickier. All right. So in order to make my life easier, I am going to rewrite a few terms. Okay. So this summation term is kind of a little bit, kind of like in a way, right? So what I'm going to do is I'm going to replace by writing recall 1 over n summation I from 1 to n xi. This is just x bar, right? So what that means is the summation of this thing is really just n times x bar. And this is going to be what I'm going to use to replace the summation xi. So I'm allowed to do that, all right? And same with this guy here, right? So these two things, I'm going to replace that by using nx bar. And the reason is here. So once we realize that, let's write it out. Summation I from 1 to n xi yi minus n x bar y bar, okay? Plus beta 1, this is x bar n x bar minus this one. I can't really change much, so I'll just copy that down. And then right hand side is of course equal to 0. That doesn't change, right? So now I'm at this spot. So the trick from here is to go back to the covariance and variance of x and see what that looks like. All right. So what I mean by that is the following. Note. So what do we have? So if you look at the summation, I from 1 to n, xi minus x bar, yi minus y bar. So I'll say note, recall covariance formula. Right, so we have xi minus x bar times yi minus y bar. That is going to give us what? That is going to give us summation. We're going to distribute this out. So xi times yi minus xi y bar minus x bar yi plus x bar y bar, right? And we're going to use the same trick that we used before. This trick here that we used before, and x bar. So what that means is we're going to distribute this xi yi minus, this is going to become summation xi y bar, but summation, we said that we can use a trick, so that becomes nx bar minus, same thing with here, right? It's just that with y, so that becomes x bar summation iyi, but this can be rewritten as y bar, and don't forget the n, and then obviously plus summation x bar y bar. Summation, it doesn't change anything because x bar y bar is constant, so that becomes n. And then you realize that there's a cancellation. There's a cancellation going on here, and here. So if that cancels out, this actually becomes summation I xi yi minus n x bar y bar, which exactly look like this part. Make sense? So this is we're gonna call it part one. So when I say part one, I'm talking about this portion. So part one. Okay. So now we're gonna continue with the you can call this sum of square. So this is recall. So next, sum of square for x, or sometimes, or you can say sample variance if that makes it easier to memorize. Sample variance. It just without the 1 over n minus 1 terms. So this is I from 1 to n xi minus x bar square. Okay, and this also can be opened up. So how do I open that up? So this is I from 1 to n xi minus 2 xi x bar plus x bar. I'm sorry, this is square here, this is square here, because it's a full square. And you can open up the parentheses. So that's oops. So that's xi square minus 2 n x bar plus n x bar. Well, x bar square is just x bar, right? So then I realize there's a cancellation going on here as well. And that makes our lives much better because that comes down to minus n x bar, which then you realize it's exactly this term. So I'm going to write that down. This is part 2, which is here, without the beta 1. So this is part 2. All right. So now, since we know the part 1 and part 2 and where they come from, right? We know this and we know this. So the shorthand notation is denote this as sxy and denote this as sxx. All right. And thus, we can solve for, thus, beta 1 hat is essentially, we can write out the formula, which is what? Summation I xi yi minus n x bar y bar over summation xi square minus n x bar square, which is here, we can plug it in sxy as a shorthand notation over sxx. Make sense? So this is where the linear coefficients of beta 1 is essentially found. And once we solve for this one, then you can plug it back, in beta 0 hat. So which is what? Beta 0 hat is y bar minus beta 1 x bar. So if you plug in this beta 1 hat, then you just get something like this. Over sxx x bar. And you can just leave like that. All right, so now this essentially is how you derive and find the beta 1 and beta 0 by using the least square assumption, which is stated here. This least square assumption. All right, cool. Any questions about this part?
No, this was clear.
Okay, cool, awesome. So yeah, so I'll post the video online and let me know if you have questions. If not, then we can just call it a day. And when I think you guys have like, if January 1st is final exam, so you guys have like, so like 1 more week before before you have final exam. So yeah, so I think we're pretty much almost there. Send me email with your questions. If not, I'll see you next Tuesday.
Sure. Thank you.
Yeah, of course. Yeah. Have a good one.